Announcements today, as far as I know. Does anyone have any questions? No, we haven't finished marking the midterm. Hopefully we'll get it back on Friday or Monday. Then we'll talk about it more. All right. So what we've been doing so far, talking about propositions and inference, is we've had propositional definite clauses in terms of clauses made up of facts and rules, had interpretation and models, we had this logical consequence, and we had two proof procedures, a bottom-up proof procedure, and we had the notion of a minimal model, and then we had a top-down proof procedure. Are there any questions about what we did, any of this? All right, good. All right, let's do a clicker question. I couldn't think of any good questions, so I just thought I'd let everyone get a mark if they wanted one. See, I told people to be worth something, so see if you can pick the right answer. I'll wait till there's 100. All right, I'll give you 3 more seconds. 1, 2, 3, stop. All right. The correct answer is, of course, C, but everyone else doesn't care about it, so I'll give the people who care marks, then we can go. The rest of you don't care. Of course, C was the right answer. All right. All right, what we're going to do today is we're going to talk about debugging knowledge bases. We're going to talk about analyzing a domain to determine background knowledge and should be asking the users. Then we're going to model a domain for a proof by contradiction. Then we're going to implement this. Hope we might get to the stage of actually talking about how to implement this proof by contradiction. So we're going to talk about different ways of reasoning about this. What we're going to do is, first of all, we're going to talk about debugging knowledge base. So what we call knowledge level debugging, of which we're going to mean debugging that depends on the meaning of the symbols, not how it's computed. Because we're going to do all sorts of different ways of computing things, and what we'd like to do is to get something that you could use whatever implementation is most efficient, but then we want to debug them according to what things mean. So what we'd like to do is to have a way of debugging them through what things mean. All the time you've thought about debugging programs, you actually look at the code and you have to work out how it's implemented. But there are some times you can debug things without knowing how they're implemented by just knowing what things mean. And that's what we're going to talk about here in this case. So we're going to talk about, so claiming there are four problems of these non-syntactic errors. The first one is we get an incorrect answer. So an algorithm that's false in the intended interpretation, we could actually derive it. So we could prove something that's false. Right, so if we prove something that's false, what does that mean? In the intended interpretation, what does that tell us about this knowledge base? So if we know that KB entails G, oh, that's awful, isn't it? But G is false in the intended interpretation, right? What does this mean? What can we tell us about this? What? No, we proved it. This logically follows from this, but it's false. What can we tell me? Well, that's just a word for it. What do you know? Yes, it means that KB is not a model, the intended interpretation is not a model of KB. The intended interpretation is not a model of right, so there's something wrong. There's a wrong statement in there. There's something wrong in the knowledge base. Right, so there must be something. There must be a false statement. A false statement. In the knowledge base. Right, so this is buggy. There's something wrong with this. This is not a model. If it was a model, then G would have to be true in the intended interpretation, so it's not. Okay, so we've got this problem, we've got this example here of we actually have a false statement, something that's false in the intended interpretation. Okay, that makes sense? So we have a bug in our program. The second one is that we have this knowledge base doesn't entail G, but G is true in the intended interpretation. In the intended interpretation. And what does this tell us? What must be held? What might happen here? Well, but it's not a positive. It doesn't follow. And if we have a proof procedure, right, we also have in K, but you can't prove G either. Right, so this one here, and we can prove G. So both of these cases we're sort of saying, not only does it not follow, we can't prove it either, right? Because we have multiple proof procedures that sound incomplete. So what happens here? There's something wrong with our knowledge base. What is it? Right, so there's missing statements in G. In KB. Does that make sense? Because you're not going to write down programs that are always correct, right? You're not going to write down knowledge bases that are always correct. But we'd like to make sure that we can find them. There's two other errors here, one of which the program goes into an infinite loop, and the other one we'll talk about later today about irrelevant questions. So it could go into an infinite loop, in which case it might not stop. So in ours, we could put in loop detection, but for the moment, it's just a problem that could arise. When we get to richer languages, it also gets a problem. Okay, does that make sense? We just got problems in here. So what we're going to do today I'm only going to talk about this correct answers produced. So an atom that's false in the intended interpretation was derived. This is actually much more tricky to do because you have to search through you have to find the place about where there's missing information. So we're just going to do this one. So now what we're going to do is we're going to suppose an atom G was proved. So we have this knowledge base that derived G, but is false in the intended interpretation. And the idea what we're going to do is we're going to find out which rule, which clause is false in this intended interpretation. That's our goal. So what we're going to do is we're going to try and look for a way to to find this thing that must be false. So if there's something that's proved but not false, well then there must be some clause. So for the logical consequence, there must be some clause, G if A1 to AK, in the knowledge base that was used to prove G, where each of the elements of the body was proved. So the only way we can get G is by using one of these rules. And if it logically follows, this must happen as well. So if it logically follows, there must be some rule, because otherwise we could set G to be false, right, and we wanted the atoms to be false. So if it's not a logical consequence, right, there must be some clause in this knowledge base that was used to prove G. And each of the AIs was proved. So what happens then? So if we do this, what do we know about? So now we're going to do this reduction. So there's a clause in the knowledge base. Each AI was proved. What do we know about each AI? Are they logically follow from the knowledge base or not? So what about these AI things? A1 down to 8, what are these AI elements? Right, so there's two cases for these AIs. Either one of them is false in the intended interpretation, or what's the other one? What's the other choice? Not free variables. There's only have this clause. Either they're all false, either one of them is false, or Well, one means more than one. One or more. One is false. There's one. What's the other alternative? Right. Either this or all of the AIs are true. Either one of them is false or they're all true, right? That's the only two choices we have. What if you have one of the false? What if one of them is false in the intended interpretation and is proved? What can we do? What should we do? Right, we've got to debug. So here we have now we have this A1 was proved but is false, and so we're now going to recursively do that. Right, so we're going to debug AI. Otherwise, what happens? Your answer? Tell me again. Right, otherwise this clause is wrong. So now what we're going to do is now we have this case. We now either have a clause, we found the bug. Right, so either we can reduce it simply or we found the bug. And so what's interesting about this is called knowledge, we'll call it knowledge level debugging. It only depends on the semantics, not the proof procedure. So now we can do all sorts of efficient, weird things to implement it. But now, because we have a semantics, we can debug these programs without knowing how it's produced. Because a lot of what we're going to do is sophisticated sort of proof algorithms, but we don't want someone to actually understand these proof algorithms to debug their knowledge base because they end up being really hairy. We don't care. We still want to use this knowledge level debugging. Okay, so that's what we're going to do here. We're only going to know about the symbols, the meaning of our symbols, not how things are produced. And in this case, in this particular case, we can just debug them by only answering yes/no questions. All right, so let's have a look at an example. I'm going to put that on that. I'm going to go there. And we have a little programming. We have a little logic that we wrote to sort of show off all these little techniques. It's sort of Prolog minus almost, but that's fine. But what we do here is we're going to do a few different things than what Prolog does. What we do is we're going to write down these clauses, and we actually find that if we look at this program, I'll load this. And there's this program, and we're going to find the bug in it. So we're going to ask this. Oh, rats, I can't copy. Ask, copy. All right. And if we ask it this program, so what I did here is I did this ask whether lit L1 is, and it said, I can prove it. So the answer here is something I can prove. And if you look at this thing, if you look at this light, it's not on. Okay? So now you are going to debug this program. The program's here. There's something wrong with this program. And I want you to find this bug in this program. And of course, you don't want to read the program. We'll find the bug without reading the program. The program's there. You can read it if you want. All right. So what we're going to do is we're going to get our clickers again. We're going to have A, B, C, D, and E. The first atom in the body is false. The second atom is false. The third atom, and E is all of the body is true. So in other words, we found the buggy clause. Okay? Let's go here. So what I'm going to do is I'm going to ask, how did you prove this? We don't know what the proof procedure is doing, but that doesn't matter. We don't really care. So we're going to ask, how can we prove this? And it's going to tell us that we proved lit L1 because L1 is a light, L1 is live, and L1 is OK. And all I'm going to tell you is what these things mean. Right? So we're going to debug this program without knowing how. All we're going to do is just to make sure we can just effectively answer yes, no questions. So L1 light means it's light. Live means there's power coming into it. And OK means it's working OK. Right, so which one of these is the first atom in the body false, the second atom of the body false, the third atom of the body false, or is the clause? We found the clause. Okay, does everyone understand what we're doing? We're looking at this diagram. We know, does everyone understand the meaning of these symbols? So which one of them is false? We just have to answer yes, no questions. Simple, right? Because we know symbols have meaning to us. Just this bottom one here. We're just going to look at this clause here. And we're going to try and say which one's false. Let's see what people have said. B. So it's not a trap. So it's a light. L1 is a light because we know what lights are. Right. But there shouldn't be power coming into it because that's what live means. Live means there's power coming into it. And we don't, well, it might as well be OK. Does it make sense? So now we're going to ask, how do we prove this? And for this language, we're just going to type in that everyone said B, so the answer is 2. And now we'll actually, oh, you can keep doing this. Or maybe I should stop and restart. Maybe I'll stop and restart it. So is the first element of the body false? There's only one element of the body, so either it's A or E. B or C are not the right answer because there's only one element of the body, by the way. So this is true, right? So I'm going to say that the answer here is 1. Let's stop this again. Let's go here. And now we're going to look at this one. Is live W0, which means there's power in W1. Sorry, live W1, which means there's power in W1. Up S2, which means switch 2 is up. So which one of those two is false in the intended interpretation? So we're going to do debugging by, whoops, okay. Start clicking again, okay. We're looking at this diagram. This is my world, okay. And now we're going to have, right, so the answer here is, the first one is true, right? Let's click that. All right, so we're going to say the answer here is, was it 1? Now we're going to have another one, another clause here that says live W1, if live W3 and up S3, so which one is, oops, let's do this. Right, so which one of these is true or false? Should live W3 be true? Up S3, is that true? In this interpretation, is this true? Okay, let's have a look at this. What do people say? So if you understand, W3 is this wire that's connected to the outside, right? S3 is up, so they're both true. So we found this buggy rule, right? Does that make sense? Just by answering yes, no questions, by knowing meanings of symbols, we can debug things without knowing how they're computed, right? You don't know whether it's implemented the top down or the bottom up or some inside out way, because it doesn't actually matter for us. Okay, so as far as we're concerned, we can debug this program without knowing how it's implemented. Okay, any questions about that? Yeah. Oh, well then we just pick one of them at random, then we can debug either one.
So when you finish the first one, then you'll have to go back and check.
Yeah, once you fixed one bug, then you go back and see if there are more bugs, right? But this one will guarantee to find a bug. It's an algorithm that will guarantee to find one. You're not going to go down paths where you're not going to find a bug, right? Because we know what everything depends on. Did you have a question? Any other questions? All right. All right, so we found the bug. The buggy rule was this one. All right. I don't know, I have to better okay this. Okay. I've got to quit that. Oh, hang on, I'll quit this. Okay. You can keep asking all sorts of things. You can keep exploring the search space in this program. All right. Oh, go away. All right. Next topic. So in this electrical domain, in this one here, we're going to think about what should the house designer know and who has the detailed building plan. So someone who's the house designer who designed the house and knows how the electrical system in this house was designed. Or and what should the occupant know? That's what we're going to look at now. So let's suppose, again, we'll do some democracy. Pretend to be democratic. Okay, so we're going to ask A, B, the designer, or the occupant, or neither. And what I'd like you to do is to imagine you asking the designer a question or asking the occupant a question and seeing what answer they give you. So the first question is the bathroom switch up? Right, so would you expect, oh, I should start this. So imagine phoning up the house designer and saying, is my bathroom switch up? What would they say? Imagine phoning up the occupant of the house and saying, is the bathroom switch up? Right, so would you expect both to know, the designer to know, the occupant to know, or neither? All right. Right, so you'd expect the occupant to know the answer to this question, but you wouldn't expect the designer of the house to know the answer to this question. Okay? What about, is there a wire between circuit breaker 7 and the bathroom switch? Would you expect the designer, the occupant, both or neither to know the answer to this? Okay, let's see. Lots of people have answered. Oh no. I wish I can do that anyway. Right, so you'd expect the designer of the building to know this, the designer of the house, but not the occupant to know these things. So there are certain things the designer of the house knows that the occupant doesn't know, and vice versa. What about, is the bathroom switch broken? Well, what might you know about this? Oh, no. Oh, sorry. Right, you probably wouldn't phone up your building designer and ask, is my bathroom switch broken? Because they would sort of give you a funny look, right? It's possible that neither would know, but it's possible the occupant would know as well, right? So there's some things here that maybe we'd like to do some reasoning to determine whether the bathroom switch is broken or not. And that's what we're really going to do in a minute. We're going to look at how we can determine this. And the other question is the house wired incorrectly? So what would you expect this to know? And the design, and it's probably the designer, but the designer probably doesn't know this either. Right, so the probably answer here is probably that neither of them know this. You know, this person's probably not on the blueprints about whether the house is designed incorrectly, right? So there's sort of different things. So what we'd like to do is to not model everything, everyone's knowledge in some monolithic sense, because then we can't do it. So what we're going to do is to make the design of the system, we're going to build a system that's going to talk about whether bathroom switches are broken. And what we'd like to do is we'd like to design the system so that we're getting the knowledge from the appropriate source. Okay, so we're not going to think about having this, the designer and the occupant are all going to tell us these things. And in fact, you were going to find out that the user, the person in the house, you can't expect them to tell you everything. They don't know what information's needed. They don't know what vocabulary to use. You can't sort of expect, there's a whole lot of people who you can't sort of expect them to tell you arbitrary things, right? We can't expect them to type in clauses. They're not going to. We can't expect them to start volunteering information. We'd like to make things as simple as possible for this system, for this user to use, right? If you have a Nest thermostat in your house, it doesn't actually get you to put any buttons because people don't like putting buttons. They don't like telling the system things. Okay, so what we're going to do again, we're going to provide information, and what we're going to do is do this very trivial thing here we're going to do is just going to make some things that are askable that they should be able to observe. So we're going to ask them questions about what it is, essentially ask them yes-no questions. So we're going to have sort of askable atoms of those that the user should be able to observe in the system. And there are going to be three types of atoms we're going to talk about. The atoms which the user isn't expected to know. Right, so they're going to ask questions about whether this particular wire is connected to this other thing. They're not going to know, right? The user doesn't know a whole lot of things, but they know some things they may know the answer to, or maybe we don't know, or maybe they don't know the answer to. So we should let them say, I don't know. We should let them tell you information. And typically you have some nice user interface, but we're trying to look at one level lower than this nice user interface. We're trying to look at what's going on underneath here. Whoops. Or answers that they've already provided information about. We don't want to keep asking them information again, so we're just going to worry about that. Okay, that makes sense. We're going to just have this ask the user. And we'll also talk about, in our top-down proof, our bottom-up proof procedure, we'd sort of expect everyone to be asked everything, right? It's sort of, you would sort of get them to ask every question. But in the top-down proof procedure, we can just ask the users about this. Once we get to an atom, we say, can we prove it? Well, one of the ways of proving it might be to ask the user. Or we could get a website or ask some sensor. Okay, so we're going to have this system where we can actually ask. Here we're just going to do it. We're going to assume the only sensor we have is this user who can ask yes-no questions. All right. So we have, let's get rid of this. I don't want that. Whoops. I don't want that. It's fine. All right, so we have this thing, and I can, let's clear this. And I'll ask another one. This ask the user one, it actually is the same as before, but what we do in this ask the user, we actually talk about just clause we're just going to add in the system. We can just say some things are askable. And these askable things, we're going to ask the user something that's true or false. So that's the only thing we have in here. The only thing we have is we're going to ask this user. So let's load this thing. And we'd like to know whether L1 is lit. Oh, that's why I shouldn't copy the whole thing. Right. And it's going to, of course, come back here. And it's going to know, because it's proving L1 is lit, right? You look at the rules for L1 is lit. It's the same code we had before. Lit L1 if it's live and it's if it's a light and it's live and it's okay. We know it's light. We want to know if it's live L1. And if we look at the rules for live L1, so we're looking so lit L. Whoops, what's happened? We have this rule for lit L1, right? So now we're going to prove light. We prove light. We need live L1. He's saying if live W0 is true with this and up S2. Right, and so now what we want to do is we now want to come along and say, is this question true, right? So now we're going to ask yes, no questions in the middle of this to actually start talking about what it is the user should know. Because we're going to say the user should know whether the switch is up. So what's the answer? What will I type here? Yes, no, pick something. Is it up? Let's say, well, the answer is yes. Let's put yes. Right, and that's going to ask whether S is S2. Is that right? Did I rename something and make an error? Oh. Whoops. Oh. Sorry, I typed the wrong thing. Someone should have, all right. What should I say here? Say no, let's say no. So it couldn't prove it for this way. So it's going to ask, is down S1 true? What should we say? What should I say? No or yes? Let's say yes. What about this one? Is up S2 true? Is down S2 true? Sorry, I can't. Well, I can ask another question. If you said yes, then it's going to prove it. Sorry. All right, does that make sense? There's something weird that's going on. What's weird that's going on? Yeah, it doesn't know. It's really dumb logic, right? So if we have this really dumb thing, it doesn't know that up and down are related at all, right? But if you're honest, it doesn't care, right? So it doesn't know that up and down, we have a very dumb logic, right? We have this very simple logic. It doesn't know about negations. It doesn't know about anything, right? But we can have this idea of this difference between this model of the world and these observations of the world. And when we get to probability, it's going to correspond again, because one of these is going to be our probabilistic model, the other is going to be conditioning, if anyone's seen probability before. We're going to get this exactly the same thing, this observing the world is different to our model. That's important to know. All right. All right, then we can ask for more answers. Is there more answers? And it's going to say there's no more answers. We've actually answered all the questions. Okay. Any questions about that? Just the idea about having some questions that we can ask, and you know how to implement it, right? In the top-down proof procedure, if it's askable, you can ask the user, right? So when we did this top-down proof procedure, instead of using a clause, we're just going to ask the user. That's all I did here. Okay, does that make sense? Yeah. It's actually similar to, I can ask, oh no, it did it. Sorry, it remembers the answers. What's the other one I can ask? Lit L2. Lit L2. And it's going to say why. And you can ask, why did you want to know this problem? So let's just explore the whole. So essentially there's this proof procedure, there's this proof tree inside it. So it lets you explore this proof tree. So it tells you that the reason I wanted to ask up S2 was because there's this rule that says W4 is live if live W3 and up S3. So you can effectively debug answers that are sort of asked that you shouldn't think they should be asked. Right, so the other question in here, the other one we had was was one of the things you can do is sort of ask irrelevant questions, and you can actually explore the proof tree again. In a similar way we explored it downwards, we can actually effectively explore this proof tree upwards. But it lets you sort of explore all the proof trees, and even in complicated programs, the idea is that there might have a big knowledge base, but there might be simple proof trees. Okay, questions? All right. All right, next thing. So in this electrical domain, what if we predict that the light should be on, but observe that it isn't? Right, so we had this problem before about what happens if we predict, if we go through here, we say light S3 is up, but L2 is not lit. What might we be able to do? What might you expect it to do? If you look at this diagram and I say, actually switch 3 is up, but light 2L is not lit, what might be wrong? What's happening? And suppose we don't have a bug in our program, but rather, what might happen? What happens when you turn a switch and the light doesn't go on? What do you think? Has anyone ever done this? Has anyone turned a light switch on and they think the light's going to go on and it doesn't? Has it ever happened to anyone? Oh, what do you do? What do you think? Right, you think that the light bulb's broken. Or maybe it's because there's power on the outside is not coming in, right? Does that make sense? So we'd like to have these other things, these other ones, not just askable, but things that we don't know the answer to. We're just hypothesizing, like the fact that things working properly. But if we make an observation, we'd like to be able to prove that it's not true. Okay, so let's go through here. So what we're going to do is we're going to work out how to model that. So we're going to expand definite clause language. We're going to include these things called integrity constraints, which are essentially rules that imply false. And false is this atom that's false in all interpretations. So false is never true. So now we have this new language in here. And what we're going to do is we're now going to make conclusions from contradictions. Now we can get contradictions. But when we had this definite clause knowledge base, when we just had definite clauses, it's always consistent. But now we can actually get inconsistencies. So we can observe things contrary to our assumptions. Right, so before it was always consistent. There was always a model before of a definite clause knowledge base. We could just assign everything to true and we were happy. We had a model. But now we can't do that anymore. So this integrity constraints, just a clause we saw before, it just has false at the head. The AI are atoms, and false is an atom that's false in all interpretations. We just have this extra special rule. And then there's something called a horn clause, which is either a definite clause or an integrity constraint. So just all we're doing is adding this one simple extra thing to our language, namely rules with false in the head. Does that make sense? Okay. But now what we can do is we can now have something that follows from a horn clause knowledge base. So now we have something. We don't have negation in our language, by the way. We can't write rules with negation in, but we'll end up being able to prove negations. So the negation of atom, we're just going to write with not A, not alpha, is true if alpha is false and is false if alpha is true. So it's just the normal negation you've all seen in propositional logic. And here's my knowledge base. If I know false if A and B, A if C and B if C, what can I conclude? So this is my knowledge base. What can I conclude? What can I conclude? I can't conclude C. What can I conclude? Well, I can prove that. What happens if I assume C? What happens if I assume C? What happens?
A and B have to be true.
Right, and then what happens?
First, constraint would be true. False.
Right, so you can prove false effectively. Right, so then we get, has anyone heard of proof by contradiction? Right, we get a proof by contradiction, right? This is proof by contradiction. We can do this. We can prove not C. Assuming C, we can now prove false. So here we get a contradiction. Okay, so now we've got this simple language. Now we've got this case here. We can prove negations, even though we don't have a negation in our language. By adding false into this language, we can now prove contradictions. We can also prove disjunctions. So the disjunction is A or B. So it's true if alpha is true or beta is true or both are true. So alpha or beta is true if one of them is true, and it's false if they're both false. There's this normal OR that we've seen before. And again, we don't have this in our language, but we can prove it sometimes. So here's an example. If we have false if A and B, and A is true if C and B is true of D, what can we conclude? Someone said it. I heard a murmur. Oh.
C or D is false.
Right, we know that C or D is false. So if you assume C or D, if you assume C and D, right, this implies false. So we can prove that not C and D. Therefore, it's not C or not D. Right? What else can we prove in here? What else do we know? What else can we prove from this one? Right, you know, C or B is false. What else do you know? That not C or not B. What else do we know? Because if we assume C and we assume B, we get a contradiction, right? If we assume this and we assume this, we get a contradiction. What else could we prove? Quick, someone else. Not D and not A, right? Not D or not A. Okay. What else could we prove? Another one more. Right, not A or not B. Does that make sense? All of these follow. When we assume something's a conjunction, we get a contradiction, we can prove that one of them must be false. So we can prove, so now we can prove the disjunctive negations. Right, so we could prove atoms and we can prove now we can prove, so now the things we can prove, we can now prove conjunctions of atoms, just like we could before, right, as with definite clauses. And we can also prove disjunctions, negations of atoms, disjunctions of negations of atoms. Okay, so we can prove both of these things. We can't prove arbitrary disjunctions, right? We can't, so far in this language, we can't prove just disjunctions of atoms. We can't prove that A or B is true without proving one or the other. Right, so we can't prove X or Y without proving one of them, without proving X or proving Y. Whereas in normal propositional logic, you can do this. Okay, so we can now prove these things in here. So what I'd like to do is, if you look at this, you'll find there is lots of different answers in here. Right, turns out once we have a contradiction, there's all sorts of different things we could prove. but we don't want to prove arbitrary things. We'd just like we had before, we'd like to have queries. But here we're going to have queries about what things we can assume. So we're going to have assumables are atoms whose negation we're prepared to accept as part of an answer. So these are the things I'm going to assume in order to get a proof by contradiction, right? Remember all your proofs by contradiction you've seen? You assume something and then you go through and you get a contradiction. The assumables here are the things that we'd like to assume in order to get a proof by contradiction, and in particular they're the things in your answer that are going to be negated. Then we're going to have a conflict of a knowledge base, a set of assumables that together with the knowledge base imply false. And a minimal conflict is a conflict such that no strict subset is also a conflict. Okay, so we're now going to have assumables, conflicts, and minimal conflicts of the answers that we could do. So if we have, so now what we're going to do is now we're going to write down what our assumables are. Right, we're going to explicitly tell the system what I'm allowed to assume, because it's not going to have arbitrary answers. It's not going to say arbitrary silly things that are disjunctions. Well, maybe this isn't, we're going to prove in our light switch that light L2 is broken or the circuit breaker is broken. We're not going to prove that maybe the wiring is wrong or something. We don't want to have it into arbitrary consideration. We just like to prove those things which we're interested in. How am I going? Oh, I still have 2 minutes, 3 minutes. So what about CD? Was this a, so remember what a conflict is? A conflict is, what happens if I prove, what happens if I assume both C and D? What do I get? If I assume both C and D, what happens? What can I prove? Well, if I prove C and D, then I can prove A and B, so I can prove false. So that's a conflict. In fact, it's a minimal conflict. I can't assume just one of them. I just assume A by itself, I don't get a conflict. I don't get a contradiction. So if I just assume C by itself, I don't get a contradiction. And if I just assume D by itself, I don't get a contradiction. So it's a minimal conflict. Right, what about CE? Oh, hang on. Oh, it's okay. So do CE. Again, that's a minimal conflict. What about CDE? What happens if I assume C and D and E? Do I get a contradiction? Right, so this is a conflict, but not a minimal conflict. And if I assume, again, if I can throw in some arbitrary thing, I can get conflicts that are not minimal conflicts. A conflict is just a set of assumables together imply false. I'm going to use those in order to have proof by contradiction. All right, let's stop there. Thanks.